this pre-calculus algebra video, we'll look at more examples of finding zeros of polynomials and related topics. What we've already done is looked at finding some zeros and using some different techniques to find those zeros. What we're going to look at in example 4 is finding the polynomial when we are given the zeros. So here we're given that I and 3i are zeros, and we're given that f of -1 is equal to 20, we can use that information to work backwards using the linear factorization theorem and find the polynomial. To start with, we want to notice that this is given that it's a 4th degree polynomial. What that means is that there are at most four factors or 4 zeros, both zeros and factors. So we know there's at most 4. The next thing we know is that complex factors and complex zeros come in pairs. Whenever you have a factor x minus I, its conjugate x plus I is also a factor. And if x plus I is a factor, then just like I is a 0, then the opposite of I is also a 0. So when I know that I is a 0, I also know that the opposite of I is a 0. And when I'm given that 3i is a 0, then I'm given likewise that the negative 3i, the opposite of 3i, is also a 0. What we're going to do is take these 4 zeros and write out the factors that those zeros deliver us. So we'd have x minus I, x plus I, x minus 3i, and x plus 3i. Let me make sure you're following where I'm getting those factors, because you might not be as accustomed to working backwards this way. But I was given that I was a 0. If I set this x minus I equal to 0, when I solve that for x, I'd get the x equals I. If I set x plus I equal to 0, then when I solve for x, I'd get a negative I. If I set x minus 3i to 0 or x plus 3i to 0, I'd get the zeros 3i and the negative 3 times I. So I can take these zeros and work backwards from that to get the factors. What we're going to do next is write those factors. We'll take those factors, multiply them together until we can develop an idea of the polynomial. So here's what it would look like. We've got that f of x is a sub n, some coefficient, times x minus, then each of these zeros. So x minus I, x minus the opposite of I, x minus 3i, x minus the opposite of 3i. I'm going to go a little overboard here in showing some of the steps just to make sure we don't lose anyone, because those factors we get are going to be x minus I, x plus I, x minus 3i, x plus 3i, and this shows how I get those. Okay, I'm now ready to multiply. So when I multiply x minus I and x plus I, because those are conjugates, I know that going backwards from the difference of squares, I'm going to get this x squared minus I squared. The first term squared minus the second term squared. And an I squared is -1. So this is x squared minus -1, which is the same thing as x squared plus a positive 1. So when this x minus I, x plus I are multiplied together, I'm getting x squared plus 1. And then when this x minus 3i is multiplied by its conjugate pair, or its conjugate rather, x plus 3i, I know I'd get x squared minus this 3i squared, so that's x squared minus, be sure to square the 3 also, 9i squared. The I squared is negative 1, so that's x squared minus 9 times negative 1, or x squared plus 9. If you need to, review that a little more and make sure you're comfortable with where those factors come from by multiplying each of the pairs of conjugates. All right, once we've done that, we could multiply our two factors together. So we've got still our constant, or our coefficient, a sub n, and then when I multiply the two binomials, x squared times x squared, so first times first, outside times outside is 9x squared, and the insides are 1x squared. When I combine those, 9 plus 1, that'd give me plus 10x squared, and then last times last, 1 times 9 is 9. I'm almost there. I know this seems like a lot. We're almost there now. The last thing we're going to do is find a sub n. We need to find the constant, the value of a sub n. And we do this given that f of negative 1 is 20. So if f of negative 1 is 20, then I could do this. I could go back to what f of x is. F of x is a sub n, x to the fourth plus 10x squared plus 9, and I know that this is equal to 20. So I'm going to replace the x with this negative 1, and what that gives us is a sub n times negative 1 to the fourth is 1. Negative 1 squared is 1. 1 times 10 is 10 plus 9. That's 10 plus 1 is 11 plus 9 is 20. So let me make just a little bit of space here to the right. So it looks like we have that 20 a sub n equals 20. So what is a sub n? If I divide both sides by 20, I get that a sub n is not 20, but 20 divided by 20, or 1. So we're ready to write out our fourth degree polynomial. Our f of x is 1 times x to the fourth plus 10x squared plus 9, or in other words, it's just x to the fourth plus 10x squared plus 9. And that's it. That's our polynomial. If you need to, that was a long problem. I'd encourage you to go back and review it a little more if you need to. Make sure you understand that. Let's go on to one last example. This example is using Descartes' rule of signs. Did you hear how I read that? Descartes is the name of the mathematician, and we assign this rule, the rule of signs, to Descartes. He's the first one, maybe or maybe not the first to discover it, but the first one to write it out. So Descartes' rule of signs tells us how many real zeros there are. It tells us how many positive real zeros there are and how many negative real zeros there are. That's going to be one more piece of information that could be helpful to us if we're ever looking to find all the zeros of a polynomial. So here's how you use Descartes' rule of signs. It's really pretty easy to apply. The tough part is just remembering what it is and how and when to apply it. But here's what we have. We have x cubed, 2x squared, 5x, and 4. Those are all positive. So it's a positive, 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 positive. This is almost a trick question, but how many times did the sign change from positive to negative or negative to positive? The answer is that there were 0 sign changes. If there are 0 sign changes, there are no positive real zeros. Let's check to see how many negative real zeros there are. To do that, we need to evaluate f of the opposite of x. So if f of x is x cubed plus 2x squared plus 5x plus 4, that was something cubed plus 2 times something squared plus 5 times something plus 4. If I replace that x with the opposite of x, be careful here. You know, it doesn't matter what the exact value is. All I'm concerned with is whether it's positive or negative. I'll go ahead and write out the entire thing, but keep in mind that all I really need to know is each term positive or is it negative? The opposite of x cubed, that's 3 negatives. So that's going to be the opposite of x cubed. The 2 times the opposite of x squared, the opposite of x times the opposite of x is going to make it positive. So that's going to be plus 2x squared. 5 times negative x, negative 5x, and then plus 4. So we've got a negative, positive, negative, positive. Let's look and see how many times did the sign change. I'm going to count those. From negative to positive, there's a change. From positive to negative, there's a second change. From negative to positive, a third one. So there were 3 sign changes. Here's what we do next. Here's what Descartes' rule of signs tells us. Oh, let me make that a little bit smaller so it doesn't. If I have 3 sign changes, let me highlight it. If I have 3 sign changes, then there are either 3 or 1 real zeros. That's what, how do I know that? It just comes from Descartes' rule of signs. 3 sign changes, there are either 3 or 1 negative real zeros. So 2 pieces. For positive real zeros, there's 0. For negative real zeros, there's either 3 or there's 1. Do you see how that could help you if you used Descartes' rule of signs? And we went back to those problems where we were trying to find the zeros. If we had eliminated that there were no positive real zeros, that would speed up our process just a bit. So this Descartes' rule of signs is helpful to just shorten our work in some cases. I hope that you've found these topics for finding zeros helpful. The best approach, the best way to get good at finding zeros of a polynomial is to jump in and practice, actually try some examples. You could start with the examples worked in this video, but then you'll also want to try the examples in your homework.